Hey guys, so let's go over some practice problems for Module 7. Okay, so our first question reads, a sample of gas occupies 1.36 liters at 25 degrees Celsius and 377 millimeters of mercury. What volume will it occupy at 390 millimeters of mercury at the same temperature? So anytime that you're doing, I guess problems for any time that you're doing problems in chemistry, right? Like anytime. What I always like to do is write down what we already know, because whenever we write down what we already know, then it's gonna basically tell us what we need to do. So let's say, okay, well, I have a volume, I know that, which I have a volume of 1.36 liters at a temperature of 25 degrees Celsius and a pressure of 377 millimeters of mercury. So what volume will it occupy? So V2 is our question at 390 millimeters of mercury. So we know that we change to P2, 390 millimeters of mercury at the same temperature. So whenever they say at the same temperature, that's already telling us that our temperature is constant. So we can ignore this value. So now we're left with PV and PV. So what does that tell you? Well, that tells you that we're dealing with Boyle's law. We're dealing with P1, V1 is equal to P2, V2. And if you didn't know how to figure that out, like even if you weren't looking at, oh, I remember P1, V1, whatever, you could have also said, okay, let me look at PV equals nRT. And you could have said, okay, they didn't give us a mole value, but they said that temperature was constant. We're not exactly changing the amount of gas, we're just changing the pressure. So that means moles wouldn't change. And then our constant is always constant, right? So we could already see that those other things are constant. And then we say, okay, well, we need to make sure that they're on the left side of the equal sign, which they are. So it'd be PV equals PV. So you can kind of derive that equation even if you didn't know how to do this. Okay, so now that you've done that, let's actually start converting our values. Because remember, we can't use them until we put volume in liters and pressure in atmospheres, right? So, okay, so let's look at the first pressure. So we have 377 millimeters of mercury. So I'm going to convert that to atmospheres. So I know millimeters of mercury should be at the bottom and atmospheres should be at the top. So now all I'm missing is saying 1 atmosphere is equal to 760 millimeters of mercury. So once I divide this, I should get 0.469 atmospheres. Then I'm going to do the same with the other one. I'm going to say, okay, well, 390 millimeters of mercury. And then I'm going to convert this. So I'm going to say again the same thing, 760 millimeters of mercury for every 1 atmosphere. So once I do this, I should get 0.513 atmospheres. So from here, I can directly plug in, right? So I know that my first pressure was the 0.469 atmospheres. My volume 1 is going to be this value, the one that we already know. So that's going to be 1.36 liters. So that's going to equal our second pressure, which was the 0.513 atmospheres. And then times V2. So let me erase this so this isn't in the way. So okay, so whenever we start to rearrange this equation, we can find that V2 is equal to 1.315 liters. So that would be your answer for this one. Okay, so let's go on the second one. So there are 0.58 moles of sulfur hexafluoride gas trapped in a non-deformable container. Calculate the volume of the gas occupied in the container under STP conditions. So okay, so this one's actually for your module, so I guess you guys are getting a little sneak peek. But okay, so we know that whenever we're talking about STP, we're going to have a value for each one of them. So we have a value for P, V, N, R, and T, right? So first of all, they gave us 0.58 moles, so we want to make sure that we put that in there. We're not going to use STP for this one. We're going to use whatever they give us. And then they want us to calculate the volume. So our volume is our question. So all that's left to do is write the STP conditions for the other one. So we know pressure at STP is 1 atmosphere. We know our constant is always the same, 0.0821 liter atmospheres per mole Kelvin. And then we know our temperature is at 273 Kelvin. So all that's left now to do is find the volume. So we can say, okay, Well, that would mean we have PV equals nRT. So I'm just going to plug in my value. So I'm going to say, okay, I have 1 atmosphere times my volume, which we're trying to find, times 0.58 moles, times my constant, and then times my temperature. So once I do the math of this, I can find that my volume here is equal to, actually let me do that on my calculator. I don't have the answer written down. So we have 0.58 times 0.0821 times 273. So this should equal to 12.99, around 12.99 or 13 liters. So that should be the answer for this one. So let's go on to number 3. The gas pressure inside a can is 1.8 atmospheres at 25 degrees Celsius. If the gas is an ideal gas, what pressure would develop in the can if it were heated to 75 degrees Celsius? So remember, we need to write down everything that we know, right? So we're going to say, okay, well, that means I have a pressure of 1.8 atmospheres at a temperature of 25 degrees Celsius. What pressure would develop in the can? So P2 is our question. If it were heated to 75 degrees Celsius. So that means we change our temperature to 75 degrees Celsius. So assume no liquid. So basically we can look at this and we can say, okay, well that means that we would have PV equals nRT, and that means we would have volume and moles would be constant, and then also our constant is constant, right? So if we want to put them both on the left side of the equal sign, it's P over T. So that means that we're dealing with Guy-Lussac's law, which is going to be P1 over T1 is equal to P2 over T2. So again, let's start plugging in, but let's also realize that we need to convert our temperature values, right? They're in Celsius and we need Kelvin. So 25 degrees Celsius, that's room temperature, so we know that this one's 298 Kelvin. And then 75 degrees Celsius is going to be 348 Kelvin. So if I plug in these values, I can say, okay, well, my P1 is 1.8 atmospheres over T1, which was my 298 Kelvin, which is equal to P2 over 348 Kelvin. So if I were to multiply across and divide by the rest, that means that P2 is equal to 2.10 atmospheres. So that would be that value. So our last question, this one's also from your module. I just thought it was really tricky, so I kind of want to go over it with everybody. So okay, consider a balloon that will expand without any restriction until it pops. If the balloon can hold a maximum of 5 liters of gas and you're filling the balloon at a mass flow rate of 3.0 grams per second of hydrogen gas, determine how long you can fill the balloon before it pops if the gas and the surrounding atmosphere is at 26 degrees Celsius. Take the outside pressure to be 0.97 atmospheres. So again, like I said, these questions, they're always so crazy. They're always, I guess, you look at them and you want to scream and cry, right? But let's not do that. Let's just try to figure this out. So, okay. So first of all, let's always write down what we know. So we have a volume of, oops, I was going to say 3, of 5.0 liters. And we have, okay, there you go. So we have, here, let me scoot this down a little bit. So we know our mass flow rate is 3.0 grams per second. That's what we know of hydrogen gas. Determine how long, okay, so volume is equal to 5.0 liters. And then we have, so I guess, okay, yeah, time is our question. So let's write down what we want to know time. If the gas in the surrounding atmosphere is, okay, so yeah, the pressure, sorry, 0.97 atmospheres, and then the temperature is 26 degrees Celsius. So, okay, so first of all, let's convert our temperature because we know that we're not going to use Kelvin. We know we have to use, Celsius, sorry. We know we have to use Kelvin. So we're going to make sure that this is 299 Kelvin, right? So now that I look at this, I'm going to say, okay, you know what? The best thing that I can do, because I know things are changing, so the best thing that I can do is know that we have to use PV equals nRT, right? Because nothing is constant, which means we're not going to be using any of the smaller laws, right? And you know this because it doesn't give you like a P2 or V2. It doesn't give you any of that. So that's how you know that. So, okay, so we have pressure. We have volume, we have our constant, and we have temperature, which means the only thing we're missing is moles, right? So that we can kind of like plug in just there. Even if we don't know what to do after that, let's just do that first, right? So I'm going to say, okay, well, I have a pressure of 0.97 atmospheres. And I have a volume of 5.0 liters. And so I'm going to equal that to N, which is what we're trying to find, times 0.0821 liter atmospheres per mole Kelvin. And then times my temperature, which is 299 Kelvin. So once I do this, I can find that we have 0.197 moles of hydrogen gas, right? So okay, so after this, I guess it's a little confusing as to where we have to go with this, right? But I guess what I want you guys to take away from here is that notice that we have grams here, right? So that means that we need to cancel out that grams in order to get our time in seconds, right? So we know that we can cancel out grams by doing some kind of conversion, you know, whenever we do like grams and then we could do grams per second, right? So that means that we would have to find another gram value, right? So if we have moles, that means that we're already halfway there, right? So we can just convert that to grams right away. So we're going to say, okay, 0.197 moles of H2, and then we're going to convert that to grams. So I'm going to say, okay, well, 1 mole of hydrogen gas is going to be 2.016, I believe. Yeah, 2.016 grams of H2. So I'm going to convert this, and I'm going to say, okay, well, this is 0.398 grams of H2. So once we have this, let's also keep in mind that whenever we say 3.0 grams per second, we can also be saying 3.0 grams per 1 second, right? Or it could be vice versa. But basically what I'm telling you here is that we can cancel out those grams to get our time. So we can say, okay, well, I have 3.0 grams per 1 second, which notice this is going to cancel our gram value and we're going to be left with time. So after I do this math, I can find that this is 0.133 seconds, which is exactly what they want to know. They want to know the seconds. So this is our final answer. So basically my takeaway here is make sure that whenever you're doing any of the gas problems, yes, they sometimes appear to be really easy or they sometimes appear to be really hard as well. But once you kind of break it down and say, okay, well, are things constant? Are things changing? Kind of think of it that way. It'll kind of tell you, okay, use this law or don't use this law. Use the ideal gas law instead, or use STP, stuff like that. I guess it kind of comes together as a big old puzzle when it comes to gas laws. So I'll see you for the last video of partial pressure.